Welcome to the massive open online course on cartographic techniques practical. Today, we will look into slope analysis using Wentworth's method. So, what is slope analysis and why Wentworth's method? Here, it provides a very systematic approach to understanding as well as classifying terrain for safer infrastructure as well as sustainable land management. Basically, it is telling us that Wentworth's method simplifies understanding our terrain and its slopes so that we can devise informed as well as better measures to protect and conserve it as well as develop it further. So, in today's session, we will be getting a basic introduction to what Wentworth's method is, how to prepare our data to perform a slope analysis using this method. The third part is of course going to be the calculation procedure, and finally, we will see a practical application part. We will see this, how Wentworth's method can be practically applied in our day-to-day life. So, what is a slope? How is it defined? A slope is the inclined surface. It is the inclined surface or angle of land measured as the vertical rise over the horizontal run. Land is basically seen in two ways. One, the horizontal part, and two, the vertical part. So, when we are explaining slopes, this is what slope is. The horizontal rise or the angle of rise of the land over the horizontal run. So, it is a very fundamental characteristic that shapes a landscape as well as influences countless decisions and natural as well as human activities. So, let us take for example, we are mentioning that there is a 2% slope, which means there is a 2-unit elevation change over 100 units of horizontally subtle angle. Okay. The difference is very minute, but when it comes to geographic and geomorphological processes, it has significant impact. So, next, what is Wentworth's method and why is it called so? Wentworth's method was developed in the 1930s. It was developed in the 1930s by someone called Chester Keeler Wentworth. He was a pioneering geologist who wanted to provide a simplified as well as systematic approach to determine the average slope. Please note, it is average slope over the land surfaces. Compared to other methods in existence, Wentworth's method looks at providing an overall or an average picture of what the slope looks like. Here, the goal was to provide simplified information, that means data which could easily be used or transferred to make informed decisions about complex terrains. In the modern context, we can consider it to be the first step to starting a project. So, this method has been widely adopted in branches including geomorphology, soil science and even engineering. So, all these fields need slope data, and Wentworth's method has been like a first step for all disciplines that use slope data in their day-to-day work. So, what makes Wentworth method stand apart? So, the points that we have here are simplicity and accessibility, regional scale application, area based averaging as well as GIS integration. So, the simplicity and accessibility part. This method does not require any specialized equipments. It requires very minimal elements, that is the basic topographic data from a topo sheet, and no complex instruments. So, this is what makes Wentworth's method more appealing, the simplicity as well as accessibility. The next one is area based averaging. Wentworth's method provides a representative slope over the areas. It provides a representative slope over the areas. It helps in reducing noise and other disturbances from local irregularities that can alter or significantly change the measurements. Third one is regional application. Wentworth's method is particularly useful for regional scale landform classifications. It is even used for hazard managements spanning large territories. This is particularly useful because Wentworth's method provides an average, or like it gives an overall picture of a particular area. Also, the final point that is the highlight of it, though developed in the 1930s, it is still compatible and integrates seamlessly with modern GIS platforms for advanced spatial analysis as well as visualization and mapping. So, these are all points that makes Wentworth's method stand apart from the other methods around the same time. So, let us dive right into the practical part. We are going to require a few materials. So, you are going to have to keep these ready. You will need a topo sheet, tracing sheet, rulers, pens, calculators and a table of tangent angles. So, like your log values, there is a table that is available for tangent angles as well. So, we are going to make use of this in this particular exercise. So, when we are talking about practical, we are also going to see how to prepare this data for the analysis, and before preparing, let us see what the sources are. So, like most geographic data, even this one has multiple sources. So, we are going to use our topo sheets primarily. The contour lines on the topo sheets will give us the elevation values. So, we will employ that. Now, we also have the digital elevation models from satellites such as ASTER. So, the next one that we have is field measurements. We can use clinometers, also properly known as inclinometers, and total stations or GPS devices for verifying the ground truth, that is measuring the elevation data directly. We also have historical data, that is the geological and soil survey records. So, another thing that we have in modern times is drone data is another major source in the modern days to procure elevation data. We also have LiDAR data is also present and provides elevation data. So, this is yet another modern method. In the modern day, drones as well as LiDAR data is also widely used. So, we will be performing this exercise using a topo sheet, and before we get into it, we need to understand our topo sheet. So, presently what you need to focus on is this. At the bottom of your topo sheet in the middle, you will find the scale that is used. If you look carefully, in most Indian topo sheets, you will find it to use 1:50,000, and here it will say it says 500 meters to 1 centimeter, meaning 1 centimeter on your topo sheet represents 500 meters or half a kilometer in the real world. So, please keep in mind the units in which your topo sheet scale is mentioned. Now that we have seen the topo sheet as well as the scale, let us see what we have to do. So, our first step is going to be selection of your area. Generally, topo sheet is divided into 9 parts. Okay. So, we will be choosing only one square from these 9. We are choosing just this as our study area. And if your topo sheet is of a 1:50,000 scale, this is going to be about 18 centimeters. So, your study area is going to preferably be an 18 into 18 centimeter grid. So, the next step is to take your tracing sheet. We are going to put our tracing sheet over the study area and copy it. Once we have performed this, we will draw grids. Please keep in mind the scale is 1:50,000 and grids are usually drawn at 1 into 1 square kilometer units or 1 into 1 mile grids. Now that we have seen what grids do, let us see what Wentworth's formula is. Here the actual formula is like slightly different depending on the values that are used in your topo sheet. If you are using the metric system, that is, if you are using kilometers and meters, then there is a slight difference with the constant that is employed. Let us see, tan theta here is the slope angle in degrees. The next here is n. N represents the number of contour crossings per mile or depending on your unit per kilometer. Then we have something we call Ci. This is contour interval. Contour interval is also constant. It is either in meters or in feet. Then we have the constant for metric units. This is 636.6. Don't worry, we will show you how we have arrived at the constant. So, the formula is the value of tan theta is derived by multiplying the number of contour cuttings per kilometer multiplied by the contour interval in meters, which is almost always provided to you, divided by the constant value. So, how do we arrive at the constant value? The value of the constant is determined by the unit of measurement that is used. If your topo sheet has units as miles and the contour intervals are in feet, then your constant is going to be .6366 multiplied So, how do we find the constant? If your measurement unit is in miles, it means it is 5,280 feet, and if it is in kilometers, it is going to be converted into meters. So, the constant is derived by dividing this and arriving at the value 0.6366, and if it is in meters, we are going to be multiplying it with 1000, arriving at 636.6. So, what if your topo sheet uses miles and feet? The constant is going to be 3361. So, all you have to do is remember the formula and keep sure that you have observed what values have been used in your topo sheet. So, let us get into it further so that we can have a clear picture. Let us start by understanding what contour crossings are in this situation. So, we all have our topo sheets, we have our contours, we have the measures or the units marked. So, we are going to be drawing grids on top of them, which is why we initially trace them, so that it is easier for us to draw without destroying our topo sheets. once we have traced our contours, we are going to draw a grid on them. As we mentioned earlier, grids are based on standard distance. It is either 1 mile or it is 1 kilometer. So, if your scale is 1:50,000, then it is going to mean your grid is going to be of side 2 centimeters, because 1:50,000 means 1 centimeter on the map represents 0.5 kilometers on the ground. So, since we have 1 kilometer grids, we are going to take it as 2 centimeters. Each square is going to be of side 2 centimeters. If your map's scale is in miles and feet, do not worry, you can use it in inches. So, you can either opt for a 0.5 inch grid or a 1 inch grid if the scale is in miles and feet. So, the next one is counting intersections. So, what is this intersection? Now that we have our grids, we can see that the contour lines cut them at a particular point. So, this is going to be a practice image. Here the grids are of ½ inch because our scale is in miles and feet. The contour interval is in feet. Okay? So, what are contour crossings? When you have a line, suppose say A and A dash here, we count contour crossings as the number of points where the contour cuts through a line. So, here we can observe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. We say 15 because here it is not cutting, it is just passing through. We say 15 because here it is not cutting through, it is just passing. So, we have mentioned the number as 15. Very natural question. What happens if a contour cuts across a line multiple times, such as here? If the contour is cutting across multiple times, this still needs to be counted. So, this will be 1, 2, 3, 4 and 5. Even if your contour cuts across the line multiple times, it still needs to be counted. So, here the count comes up to 18 contour crossings. Next, we have density interpretation. The larger the number of contours, the steeper slopes you will have, and fewer number of contours suggest more gentle terrain. So, let us get into it. This is our practice data. Here the measures are in miles and the contour intervals are given in feet. So, this is around 5 inches. The total length here is about 5 inches and vertically this is about 3 inches. Moving on to the second step. Now that we have our practice data of sides 3 and 5 inches, it translates to 3 miles and 5 miles on land. So, we have drawn a grid system. This is 0.5 inches, meaning this is half a mile on the real ground. If your maps have used the metric system, that is the meter and kilometer scale, please keep in mind, if you are taking 1 centimeter, that is half a kilometer on ground. So, you need to be using 2 centimeter sided squares if you are going for a 1 kilometer grid. Once we are done with this, so to create these grids, you are going to use your ruler, see what the lengths are and divide it equally. The next part is the calculation procedure. Once we have marked out the number of contours here, so this is our horizontal line A and A dash. Here we have counted the total to be 15. Then we have B, B dash, the contour crossings as 18. Then we have C where we have 20 and so on. So, we do the same thing for our vertical lines as well. Here we have named them using the smaller A, A dash and counted the crossings to be 10. Then we have B, B dash where the count is 8. Then C and up to K, K dash where the last count comes to 8. Once we have counted this, we draw up a table like this. These are our horizontal lines, the capital ones, and we have marked it as 15, 18, 20 and so on. And we will go on entering it as we count into a table. So, this table is specifically for the horizontal lines. So, we will continue till G and we will keep entering it into the table as we count. We will also repeat this for our vertical lines and we will keep entering the values of the number of contour cuttings or contour crossings as we count. So, where did this come from? What is this length? Very natural question. So, the length that we are measuring here is this. If we have 5 inches, like we said earlier, it translates to 5 miles. If you remember the formula that we showed earlier, you will remember that we also need the average contour cutting values. So, to find that, we need the total length of the grids as well. So, since each grid is of uniform length, say here each line here is of 5 miles. So, we have 1, 2, 3, 4, 5, 6 and 7 lines that are 5 miles each. So, we have entered that into our table here and we have totaled it here at the bottom. What we have next is the vertical lines which are 3 miles each and there are 11 lines totaling to 33 miles. We will also total the contour crossings separately for our horizontal lines as well as our vertical lines. Then we move on to step 4. What we have to find out now is the number of contour crossings per mile. That is, we are going to find an average value. First, what we need is total length of horizontal and vertical lines. And as we have here, the total length is 35 for our horizontal lines and 33 for our vertical lines, which we will add here to find 68 miles. Next, we have the total contour crossings. We have counted our contour crossings here. The tally for the horizontal is 94 and the tally for the vertical is at 108. We have entered both to find a total of 102. So, to find the average, what we do is we divide the total contour crossings, that is we divide 202 by total length of the horizontal and vertical lines. So, here we do 202 divided by 68, arriving at a value of 2.97. What do we do next? So, to arrive at the slope value, the formula that was given to us is tan theta equals number of contour cutting per mile, that is the average number of contour cuttings which we found out to be 2.97 multiplied by contour interval in feet. So, since our topo sheet represents its values in miles and feet, the interval of the contours is 100 feet. So, we are multiplying 2.97 with 100 and dividing the whole with 3361, which is a constant that was given to us. So, once we have arrived at a value, it is 0.0884. When we had mentioned the materials, we mentioned a table of tan angles. So, this is where the table of tan angles is going to help us. So, here the value we have derived for theta is 0.0884, and here using this table we are going to find the value for this particular angle. Here we have only arrived at a value that is not in degrees. So, when you are mentioning slopes, we usually measure it in degrees and minutes. So, we have only arrived at this value and it is not in degrees right now. So, we will be taking the help of this tan angle table to convert this value that we have obtained into degrees. So, what we have is 0.0884. We are going to find the closest value here. The closest value is 0.0875 at which means it is an angle of 5 degrees. So, from our calculation what we have arrived at is 0.0884, which translates to a 5-degree slope. It translates to a 5-degree slope. So, why do we measure slopes and why is it in degrees? So, if you have used a protractor, you will know how it measures angles and slopes. So, the same principle is why we express slopes with degrees. Here, once you get slope values, to interpret them, slopes are also classified based on the angles. There are multiple classifications available. We will just look at the very basics right now. So, what we have is the first class, which is 0 to 5 degree slopes. So, these are the gentle slopes. It is ideal for agriculture, suitable for most construction activities and developmental projects. Also, it is under the most minimal risk for erosion under normal conditions. Also, it is easier for developmental activities to access such gentle slopes or gentle sloping lands. The second category is moderate slopes. Here what we see is that the lands become slightly steeper. If this was 0 to 5 degree slopes, this is what 5 to 15 might look like. So, the slopes start getting slightly steeper. Even though that is the scenario, it is still considered moderate. So, this is what our hill areas might look like. So, it is still manageable for construction provided proper designing goes in place, and it requires considerations or serious plans to execute proper drainage activities without putting too much pressure on the land. Then we have moderate measures for erosion control. So, those are required in the second category, which is moderate slopes. So, now we have the third category, that is steep slopes. These slopes are usually that are higher than 15 degrees. Here the slopes are more at risk for landslides and erosion. It is also not very suitable for construction or developmental activities. What we have next is that such kinds of lands require stabilization measures to hold it steady, unlike the first two categories. Construction, as I said, is limited and such areas are best suited for conservation activities of forests and the likes. Limitations and disadvantages. Earlier at the beginning, we saw the merits or the advantages of Wentworth's method. Now, we will see the limitations for the same. So, like any other analytical method, it has also got points or constraints that we have to consider. One is the limited resolution. Here, the data is less precise for very small terrain. That is, if we are taking the whole of this, for example, consider this is your study area. If we are taking the whole of this, it might give us better results. But if we were to consider a very small parcel like this, there might be very serious variations in case of variable microtopography, because this is considered at very small levels. When you are doing it for very small areas using Wentworth's method and trying to derive an average, what happens is the disparity or the variation becomes very high and not really representative of the terrain. What we have next is oversimplification, and by oversimplification what we mean is this particular grid might be of low or moderate slopes, whereas the whole area together might be of a moderate category. So, when we are employing Wentworth's method, what we are doing is deriving an average. So, with the disparities and with the errors that arise with microtopography, what happens is when we take an average, it might not truly represent the actual complex nature. What we get is only a very limited overview, that is overly simplified, and the specific characters are often not accounted for. Next, we have data dependency. What is data dependency? Here, using Wentworth's method, it relies heavily on the quality as well as the resolution of the data that we input. So, if we have like really old topo sheets where the lines are not clear, or if we have difficulty differentiating where it is just passing along and not cutting through, in such cases we are going to have difficulties. Also, if your contour lines are very close to each other or there are a lot of those, then again we are going to have trouble finding proper or accurate results. Last part, it is static. Wentworth's method is not something that will allow you to study change as it happens. So, it is not designed to study the dynamic slope stability or like what your modern GIS does. So, Wentworth's method is better suited for something that does not change too often or something that does not involve studying real time changes. So, these are a few of the limitations and disadvantages of Wentworth's method. We will wrap up after we take a glimpse at the real use cases, like the real life use cases. So, the major processes where Wentworth's method serves as a first step before further modern studies are performed, it involves land use and agriculture. So, as we looked at, there are three major classifications of land. We have low, moderate and steep slopes. So, when we study these, the lands that are usually low or moderate are better suited for performing watershed planning or farming activities, and according to the values we receive, plans for these activities as well as conservation can be made. So, agricultural lands are usually lower lying and of very low slopes. Wentworth's method is a first step at studying the basic nature of your land allowing you to better perform your chosen activity there. Second one is road and pipeline transmission and alignment. So, when there are roads, we often see that those are dug up for pipelines for gas or sometimes for telephone lines or internet lines. Even in such cases, the slope of the land plays a major role in cost cutting as well as the speed at which it is completed. So, again, Wentworth's method is a first step in this situation as well. What we have next is hydrology and hazard management or assessment. Depending on the slope or the nature of the area's slope, a particular area can be categorized as at high or low risk for issues from runoff, drainage or flood as well as debris flow potential. So, understanding a particular land's slope nature allows us to plan ahead and be prepared for what kinds of risks or hazards lie in wait for that particular region. Then one final case that we will take a look at is urban and regional planning. In this situation, again, urban areas always tend to develop wherever they can. So, in planned situations, what happens is the surrounding areas are studied, the terrain is studied and it expands into low lying areas or moderately sloped areas. Once the land is studied, low lying or moderate areas are chosen for development to extend further into. That will be all for today's session. Thank you. Have a wonderful time ahead.